So the last set of reactions we're going to talk about that use alcohols are called oxidation reactions. And you're going to find out that in the scope of things, oxidation reactions are among the most important and the most used reactions that we're going to talk about in all of organic chemistry. So in order to understand oxidation reactions, we're still starting with an alcohol. So we're still talking about alcohol chemistry. We're interested in turning alcohols into some other functional group. And here, our ability to do oxidation reactions depends on what kind of alcohol do we have. Do we have primary, secondary, or tertiary? And remember, that's why we did these designations. Even though all three of these species are alcohols, they are slightly different. And we're going to find out that they have different reactivities. There's some reactions we can do to them, some reactions we cannot. So remember, with the primary, secondary, and tertiary designation for alcohols, we are saying how many carbons are attached to the carbon that's attached to my oxygen. So this is the carbon attached to my oxygen. It's attached to one other carbon, primary. This is the carbon that's attached to my oxygen. It's attached to two other carbons, secondary. This is the carbon attached to my oxygen. It's attached to three other carbons, tertiary. And whether an alcohol is primary or secondary or tertiary, that's going to have an effect on our reactions. So the next thing we want to talk about is our primary oxidizing agents. And here, this is something else I'll tell you. We tend to talk about fundamental reagents. There's actually a lot of different reagents that can do these reactions that we're going to talk about, but we're just introducing you to the fundamental ones. So these are our reagents. So we've talked about reagents beforehand. You need to understand the name of these things, and then you need to understand what do they do. And the two primary ones are called potassium dichromate and chromium trioxide. And what they do is they oxidize things. Along with these, both of them are used in conjunction with sulfuric acid and water. So you'll have like CrO3 plus H2SO4 and H2O. When we have those combinations, we are undergoing an oxidation reaction and we're converting our alcohol into some other functional group. So when we look at this, when we undergo these oxidation reactions, so these reactions that we're talking about here are corresponding to our potassium dichromate and chromium trioxide, we are converting our alcohols into a different function group. If we are starting with a primary alcohol and we do an oxidation reaction, we form a carboxylic acid. A secondary alcohol, we form a ketone. A tertiary alcohol, we actually get no reaction, and we'll see why that is. So here, we're still worried about converting our reactants into our products. And so we need to understand, what do I need to do to my primary alcohol to make it look like a carboxylic acid? So here, let's look at the first one. I'm starting with a primary alcohol. So when I look at this, I see my oxidizing reagents, chromium trioxide. I say I'm doing an oxidation. The first thing I want to do is go, what kind of alcohol do I have? And so this is a primary alcohol. And this one's a little tricky. My carbon attached to my oxygen is attached to one other carbon. So this is primary. These other carbons don't matter at all. So when I understand this, when I do an oxidation reaction to a primary alcohol, what I end up forming is a carboxylic acid. So here again, there are two parts to our reagent. There's the part that actually undergoes the reaction, and then there's some other stuff that comes along for the ride. The part that undergoes the reaction for oxidation reactions is always the carbon that's directly attached to the alcohol. So this carbon is going to change in between the reactant and the product. The rest of this just comes along for the ride. So this whole bottom part is exactly the same in the product. I don't have to change anything. Whatever is attached to this carbon that is attached to my alcohol, it doesn't change. It comes along for the ride. As for this carbon, what I need to do is I need to convert it between a primary alcohol to a carboxylic acid. And remember, a carboxylic acid means a double bonded oxygen and an OH. So what I literally do is just kick out these two hydrogens and draw a double bonded oxygen on there. It's really that simple. There's no magical way of, doing this conversion. It just literally says I need to convert this carbon into a carboxylic acid. The easiest way to do it, and this is actually how I do it, is I remove these two hydrogens and I draw in a double bonded oxygen. Problem solved, full credit. So here, one other thing I want to point out is this carbon is been oxidized completely. So there is as much carbon bonded to oxygen as we possibly can. So this is as oxidized as this carbon can get. It's doubly bonded to one oxygen, singly bonded to another oxygen. And we're going to see where that's a difference. So here now, dealing with a secondary alcohol. The carbon attached to the oxygen is attached to two other carbons. That makes it a secondary alcohol. Secondary alcohols become a ketone under oxidation conditions. So notice here we were using chromium trioxide. Here we're using potassium dichromate. It doesn't matter. The reactions do the same thing. They're just two different reagents that do the same thing. Here now I got to convert my alcohol, my secondary alcohol, to a ketone. So remember, this carbon and the oxygen associated with it is going to undergo a change. Anything else attached to that carbon just comes along for a ride. It is unchanged. So in this case, what I do is, sometimes there will be another hydrogen portrayed here. I remove this hydrogen, that hydrogen, and I draw a double bond across there. It is as simple as that. I need to convert this secondary alcohol into a ketone. And that's exactly how I do it, is I remove the hydrogens and I draw a double bond across there. So with a tertiary alcohol, you can see that there's no reaction. So tertiary, the carbon attached to the OH is attached to 1, 2, 3 carbons. That makes it a tertiary alcohol, where there's no other way I can increase the oxygen content on this carbon. I can't draw a double bond between this oxygen and this carbon because that will give my carbon 5 bonds. And there's no easy way of breaking a carbon-carbon bond. So this oxygen really has nowhere to go. So a tertiary alcohol does not react with an oxidation type reaction. And that's something that's important to remember, because I really can't increase the oxygen content of this carbon. There's nowhere to go. So a couple of exceptions to these rules. So remember here we're talking about chromium trioxide and potassium dichromate, and we understand what they convert into. But when we looked at the primary alcohol, we went all the way to a carboxylic acid. During this, one of the other oxygen containing functional groups, or containing a double bonded oxygen, is an aldehyde. And so to start with a primary alcohol to make an aldehyde, we can't use these reagents. We can't use these oxidizing reagents, because if I run it, it will convert into a carboxylic acid. So in order to make an aldehyde, we still start with a primary alcohol, but we do use a different reagent. And what ends up forming is an aldehyde. So the different reagent is called Pyridinium chlorochromate. So same idea. I'll never have you guys draw this, but you can see it has the base oxidizing agent, chromium and 3 oxygens, but it has this extra piece attached to it. And what that does is it weakens the ability of the oxidation reagent to oxidize things. So it's kind of like we get a partial oxidation. So here we use abbreviations, and abbreviations are very common in organic chemistry. Nobody calls this pyridinium chlorochromate. Everybody calls it PCC. And this is a reagent that's very specific for converting primary alcohols into aldehydes. So I'll never have you draw this whole thing out, but you should be able to identify it. If I give you this structure on an exam, you should be able to use PCC. And you'll see this again, if there is an abbreviation for some reagent, I accept the abbreviation as a correct answer. So if I give you this structure on an exam and say, what is this? You need to come up with PCC. Here, some of the times there's a specific solvent that they use, so we're going to begin to see this. There's a lot of different solvents in the world. When they include a solvent in with a reaction, typically it means we must use this specific solvent. So methylene chloride is the solvent that we use during our PCC reactions. It's not fundamentally part of the reaction, but if we don't use methylene chloride, there can be problems. So you're going to see this solvent listed below the arrow, and it's just something that we include with it, and you don't really need to pay too much attention to it. So here we see our primary alcohol, just like before, and when we used stronger oxidizing agents, what we ended up forming was a carboxylic acid. Now, because we're using PCC, which is weakened, and then here is our methylene chloride. This is just a solvent that we put below it. PCC is the real reagent. What we end up doing is forming an aldehyde. We don't do a complete oxidation in this case. We only partially oxidize it. So same deal, this carbon is the center of our reaction. This is where things are going to be going on. And just like what I did with the ketone, how I convert a primary alcohol into an aldehyde is I remove one hydrogen from the oxygen, one hydrogen from the carbon, and I draw a double bond across there. It's as simple as that. So this carbon is this carbon in my product. We go from CH2 to CH, so there is one hydrogen left over. So I kick off one hydrogen from the oxygen, one hydrogen from the carbon, and I draw a double bond across there. That's not the mechanism, but that's the steps that I use in going from reactants to products. So one final reaction, just on the side, yeah, we could possibly convert aldehydes into carboxylic acids. All that we need to do in this case is to use our oxidizing reagent like potassium permanganate, and then this will convert our aldehydes into a carboxylic acid. Here again, there's a complex mechanism for this, but in terms of going from reactants to products, all I need to do is replace this hydrogen with an OH, and I've successfully converted my aldehyde into a carboxylic acid.